Hello from my side. Since Pavlos and Alessandro already started where they come from and how we crashed into each other, I finally do a little bit the same. But I haven't prepared any fine slides, so you only have to listen.
There's a marker behind you.
Yeah, no, not today or not yet. So basically, the first time I actually heard about healthcare was when I was sitting in Tropos at Germany in Leipzig. And Ulla Wanninger, so basically, many of you might know, said, okay, the same then to Pavlos that time, yeah, it didn't make it 2012, where basically I did my master, but 2016 it will fly. And I basically never thought that I would work with healthcare at that point, actually, again. I think a year or two later, we met in a summer school, and also where I met Katja in a summer school. And actually the same year I met Athena here, the first time in Athens. And that's basically how I start to know a little bit more in this community during the PhD time, basically, that I did in the TU Delft in the Netherlands. And then after I finished my PhD, I started working with Pavlos on projects, and basically where the starting project here is listed, it's FRM for radar.
Oh, very quick. I did this too. I actually put it there. I actually clicked it.
I'll try to.
Yeah, I'll move it. But it doesn't break. I have tried.
Okay.
Sorry, thanks.
So I started working with FRM for radar with Pavlos, which is a demonstration network funded also by ESA to look how we can basically make the best use of ground-based networks and ground-based systems for cloud radar validation from space. And out of these projects, there was a second phase, and then even the ACPV project. And out of all of these developments, basically, we end up with what I will tell you now, which is this Orbital radar tool, which is producing level 1 data from EarthCare or from all kind of CPRs, because it's quite modular and you can change it to now. So I start with a little bit motivation, which comes out of these times from the previous project, and then in which direction it developed. So basically the main idea of this whole simulator was, okay, well, how can we already look into the sensor behavior and look how we can use ground-based data best for the satellite validation, and play a little bit around. And one of the big things we have is we have, for example, now ground-based networks like here, Actis, but we also have radars on airplanes and the data are lying around. So basically we can make advantage of this huge data set and play around and use that for making possible advantage of this data and basically put it into EarthCare view and learn how the sensor would act like, and also look how the radar will behave and then compare it directly to the ground-based measurements. So that's basically one of the things. And the idea here was that you can basically use the ground-based systems. Here is an example for Actris. But there's also, as I said, already existing airborne campaigns lying around. For example, here, that's the system where we in Cologne mainly work with. That's the Mirac A, and then we mainly have flights over the Arctic. And the third thing that we have is that you could also forward simulate your, for example, the American weather prediction output using RC-Sim or Panther, which is another forward simulator, and then put the output when you have a radar from either space or from ground, and then put it and look like how this scene would look like measured by EarthCare, for example. One advantage of the already existing data sets usually is, first of all, you have a network, so you have like multiple stations. And then some of these networks already look into data quality management. So you know, is the sampling is set the same, there is maybe the processing the same, the data quality management, and so on and so on. And that's basically an advantage. So you can basically download these data sets, you know what they did, what they didn't do, and either plug them directly into the simulator, or you know, okay, they didn't look into calibration. Can I do that myself or not? But that's basically an advantage of these well-documented data set, for example, from networks. And that's here at the moment just one thing for Actros network. And then something for FIM for radar, where we looked into was this calibration of the instruments using stability and looking into how can we use that for distrometers. And we also looked into how crucial is Doppler velocity accuracy. So basically, do we really know in which direction usually we assume that all the radars in the network point vertically upwards, but do they really do that? And if they don't point vertically, how much is the error of the Doppler velocity? Because we want to use that for comparison, we should have an estimation of the error, or if we can directly use that. And the last point here in the middle block is there's also some of these, for example, the cloud net in Actros is already a harmonized product for target classification and some other things. So we can use that also directly from these networks to look into, for example, level 2 product evaluation. And that's basically what this tool is all about. So we have the motivation why we say, okay, that's cool to use. And we want to make it easy. So basically you use in one of these inputs, we have either, for example, Actros, the arm is missing here, sorry for the typo. Then we have the GEOM data set, which was requirement by ESA during the FIM project. And then we have 2 airplane examples, which you can directly put in. And the output is basically synthetic CPR level 1 data. And we try to also be realistic for the noise and error estimation of these products. And as an example here,
before published that it was level 2 data, but
I don't have any retrievals. It's really just reflectivity and Doppler velocity.
But without all these problems that Pavlos was mentioning, so they could consider it.
There's the best estimate, and there is the noise. So you can basically use whatever you like out of the output. I will show step by step. And basically that's what you get out. So that's the measurement from the ground, radar here from Joyce, from just one of the example days. And that's if you compare 1 to 1 already, the output in the same time frame. What you can already see is here is this ground echo that blocks quite a lot of the ground things, and you see also that it's smoother, it misses some of the smaller pixels, but you'll see that in more detail. Yes.
The second plot comes from the first one?
Yeah, that's the input data, that's the output.
Without the noise.
No, there is noise added. That's the input, that's output including noise.
Because they look smoother than the real data.
Yeah, that's because of all the smoothing of the 500-meter poles of.
Okay.
Yeah. So basically, that's the high resolution, the highest resolution you can compare your healthcare data. I will basically guide you step by step how it looks. So just in a short very short overview. That's how the code looks like in a flow diagram, just completely an overview what the whole code basically does. It mimics the surface echo, so basically it artificially introduced that. Then it more mimics all the characteristics here as an example for EarthCare, for like resampling the data using the weighting functions that mimic the pulse shape of the radar. Then you can integrate the data, you can change the integration length of the data if you want all of these things. Then yeah, what we have already implemented is we have a logging configuration for CloudSat, so you can basically use the same code and configure artificial CloudSat data. You can get the EarthCare that's there, but you can also start to play around and whatever, change the PRF as you want. You can change the integration length on prep, you can change the range resolution if you like. If you're interested, we can also play a little bit around that tomorrow also. What we have also here is the Doppler velocity errors or noise, however you want to call it. So due to satellite motion, non-uniform beam filling, antenna pointing, and the folding of the Doppler velocity, so this Nyquist range also plays a role, so that's all there. And something that we also put in is there is a conversion from 35 gigahertz to 94 gigahertz, because some ground-based cloud radars run in these frequencies, so there's a frequency conversion that it basically matches the EarthCare frequency or the CloudSat frequency. Then now I just talk a little bit more about what we do when we start. So basically it comes to these data preparations. So you see that there's two values that we feed in, the reflectivity and the Doppler velocity, which comes from whatever you define, the airborne data, the ground-based or the forward simulation. The first thing that we do is we convert along the time axis to using a constant wind speed to a long track distance. For the airborne data, it's really the along ground flight speed from the airborne system. The second thing that we do is we introduce the surface echo. It's like a very small or two bins that we do, and basically the stretching over the whole 500 meter line zone is done in a step later, where we basically go into the long track convolution and something like that. So basically we have like more or less fixed ground echo, which is then stretched by the mimic of the antenna weighting function. Then something what we also do is that there is this geom data input file, which is mainly the files that ESA asks us to provide input in, and it has some advantages. For example, it has sometimes much higher temporal resolution than the Arctis data. The Arctis data come with a common grid of 30 seconds, and here you have like sometimes profiled 3 seconds, so you get like a much higher resolution. And if you want to really look if these fine structures are still in your EarthCare synthetic data, sometimes it makes sense to have the real input. And if you use...
Where are these come from? Where are these geom come from?
The geom was developed during the FRM for radar. So the ESA asked us to provide a radar template for their data centers.
What data what data they are from?
That's the input data from ground-based radars.
Okay.
Then sometimes, so the next step is we do some regridding, because some of the data sets, if you use, for example, the geom data, they have several different grids and different heights and different time samplings. so that we have like a homogeneous data set that we can work easily with. We do some small regridding, and if necessary, we do this conversion between 35 to 94 gigabytes. That's all done there. Yeah.
The cost of horizontal link speed.
Yeah.
Typical is this. So do you expect a constant horizontal wind speed, or in our case, for example, when we use this, for example, for real measurement, and we have a model, if we have a model or a radius of, then it's...
Yeah, you can either use the mean constant horizontal wind for during all
in the vertical constant.
Yeah.
So in the vertical.
Yeah.
And this is something typical, you find typical that you have a constant.
No, it's not. It's an assumption that we do to convert time to space for one profile. We know that it's, we know that the wind isn't constant from the ground till whatever. The tropopause, but it's an assumption we have to do to convert each profile time. Because usually you measure time as is in the LiDAR, you have like the time axis, and you want to convert the time into range. You have like the resampling later, and one assumption we do is the constant horizontal.
I thought you put it there so that you add it in the data.
No.
But you have to, okay, no.
I need it as an input to convert time to range.
Okay, so it has a very minimum effect on the outputs in the end.
Yeah, it can have an output. If you put 10 meters per second in, it might look different in the end if you do 100 meters per second to convert time. Of course, that input or that influence you have. Then we come to the along track and the range convolution. So basically, these are outputs of the paper I listed below. And what you basically see is for the left picture, it's the 3D looking from top, how the along track weighting function would look like. So it's basically a 3D Gaussian distribution, which we basically only use for 2D. So basically use that. But you see that for the beam, so for the right plot here, it's the normalized weighting function for a long range. And you see that there is a difference between the assumed range weighting function for CloudSat, which is the red curve, and the blue one, which is for Earth carrier. And so basically the one for Earth carrier is not looking Gaussian. It's basically a little bit asymmetric. And these two basically make the change if you select, of course, Earth carrier weighting or the CloudSat weighting, and then of course also the range of these pulses is a little bit different. But these basically is taken into account, and you can basically choose which one you like. Then a little bit how these steps are basically going to be done. So it's a little bit summing up of a long track, then the integration, and then the range convolution. Basically, the first step that we do is these along track convolution things. So we know that these weighting functions of the antenna along track looks more or less Gaussian. So basically, we take each of the original time samplings or range samplings of the input data and do these convolution for each of the time steps or range step, whatever you want to do. Then basically we have like a new sampling profile. Do we have like a pointer or something? Oh, we can do it here. So basically we have a new profile here, which consists out of samples depending on the weighting function in the original grid, all of these things. The next step that we do is, okay, we now make an integration. So we know that the integration for Earth, for example, is 500 meters along track. So basically we sum up all of the individual samples from the first step after 500 meters, and then we get the original range data, but still in the 500 meters sampling. And the last thing that we do is we do the range convolution. And basically there now we get the 100 meters, or for clouds that I think it's 240 meters or something like that, range bins that you in the end have. And that's basically your synthetic data in the right, a long range and a long track and a long range thing. How does it look like in a more way to give you an idea? So basically here on the top row, you have the input data as measured from ground. Just here as an example, and then a very a little bit a snapshot of the data you saw already before, but just cut here between 280 and I don't know, 300 something kilometers. So that's the original input data, and basically after you do the convolution along track, so that basically go take this step, you already see that these weighting or this antenna function, you see that it already smooths a lot of the things. You see also that what Carlos said here, if you have these very thin clouds and you have these 500-meter pulls, you basically fill up some of the spaces with a weak reflectivity. So the next thing then is you have these, from the first thing, like the long track convolution, you basically integrate in 500-meter profiles, and you see that also the resolution along track gets shorter, so basically it gets more pixely. And then finally you get also long range convolution. Instead of having, I think, the 30 meters in the original data bins, now you have 100-meter bins. And you'll see again that also some of the high things get smooth, some of the bins also get removed, because then in the end, before we have the final step, there's also like a clipping to these minus 35 dB. That Earth should have. Exactly, that's again an overview. And basically when we have come up to these two, there it is. So basically we are now here at this thing. So basically we get the best estimates from space you can somehow imagine, having the Doppler velocity and the reflectivity from space, so basically without noise here. And then the next step is basically how we treat the noise and what to do there. And also we estimate some of the quality checks or some kind of estimates for non-uniform beam filling, multiple scattering, and then also folding of the Doppler velocity.
So yeah, it's what's including noise, the third panel.
Yeah.
Identical to the second one.
Yeah, because the statistical noise we put on top of reflectivity is plus minus 3 dB, and I guess that the used radar reflectivity bar here has two huge steps to see really the influence.
Like you go small differences, like here,
There's really small.
small differences.
Why do you say plus minus 3 dB?
Basically, the noise floor that we use for.
You could see the noise when you're close to the noise level.
Yeah.
I mean, I don't see. I mean, if I look at those tiny clouds in gray,
Yeah.
I should see something there. I don't see anything. And
That's right.
So because this is including noise, but then you have subtracting the noise. I don't understand this figure.
No.
How do you produce that figure?
That one here.
Not the bottom one. Let's read
That one here. Add something on top. You
What
should
would you
see
add?
as a random so a random distribution of reflectivities for plus minus 3 dB.
Well, I cannot be
As a-
3 dB. No way.
Why?
Because it's not 3 dB.
Yeah, I
First of all, I mean, the noise depends on where you are, right? Depends on the scenario itself.
yeah.
So the noisiness of your measurements depends on the SNR of your measurements. The
Yeah.
SNR is very high when you are in the red, and the
Yeah.
SNR is very low when you are in the blue.
Yeah.
So you should have much more noisiness when you are in the blue, which I don't see.
Yeah.
So I don't think there is any, I don't know what they have done, but I don't think it's.
That's why also in the first plot it was not visible the real noisiness of the FTR data, and it was more smooth. You would expect the final synthetic to be more noisy than the original data. I would expect to see more pixels noisiness.
I completely agree that there's something that we have to look into, and I also found out that some of the noise that we add, or some of the noise that.
First of all, the noise depends also,
Yeah, yes,
the noisiness
Yeah.
depends on the SNR.
Yeah.
And depends also on the averaging you're doing. Because in fact,
Yeah.
the averaging is what beats down the noise.
Yeah.
So now I don't know, because this is maybe, I don't see anything because we are integrating already how much here?
500 meters.
Oh, meters. You should.
I completely
In
agree.
the very low reflectivity, you should see something that is different from the mid band, because otherwise.
I completely agree, and I just found out on Friday and Thursday that there's something in the plotting and in the calculation.
Yes.
Yeah. I know.
See, first of all, I don't think we use it. We use it as a function.
Yeah.
Adam and another generator. But the color scale, you don't want to see that. You can see after very low reflectivity, small changes, but to change the color, it used to go 6 dB different there. So very few points will change by 6 dB by other.
The gray and the, okay, well, I don't know.
So,
the color bar has only 8 colors, so the dynamic range.
Okay.
I think Alessandro is right that first of all we have to really look into, because I figured also out that I might be either it's only the plotting a problem, or really that something isn't added for the noise, because we have the same problem for Doppler velocities with the satellite motion speed added to the Doppler or without, and they also look really, really similar, and there must be also something wrong. But I just figured out on Friday that there is something, and I didn't have time yet to dig too much into the code. But you're right that there is something that looks not as it should be.
Okay, the other thing is I didn't get how you correct or you don't for the attenuation from the hygrometers.
We don't do any high-to-meteor or attenuation correction because we couldn't agree on which one to use and how to do it.
So basically, you are saying that basically this will not work when, as soon as you have attenuation due to liquid,
Yeah.
then it doesn't work. I mean, of course, you cannot reproduce the stage bond from the ground.
Yeah.
But it has to be a caveat that has to be clear.
Yeah, for sure.
So I mean, this lot, if you look at the stuff that is in the dark red, well, this is not how the stuff from space will look like, right?
You're right. And the second thing, it's also, so at least in the data and also in the ground temperatures, there was all freezing the whole day. That's why I want to use these thing. But you're right, as soon as we have liquid precipitation, we have to be really clear how to use the simulator and maybe discard all columns where we have liquid. And then we can still use some of the simulations to look into, but
I thought we're doing that already. Don't have it flat, goes through the day. It says which part is good and which part is not supposed to be used.
we don't have any precipitation flagging.
I think it would be useful. So I mean, in general, to have a flag where this can be trusted, the conversions can be trusted, and where it's not to be trusted.
At the moment, it's not in. Yeah.
Lucas, is there more work that will be, is there more effort for that? For example, maybe in this or it's something that is just concluded? These upgrades that now we're discussing, is there a framework for this?
No. So like a funded framework, there isn't. There is more like, if you use it, feel free to let us know what you changed, and then we add you to the GitHub repository and you can play around and add and do stuff. But at the moment, I present how it is at the moment in GitHub, and I know that there's things that we still have to look into and that we might find out. And that's also something maybe in the next 2 days we can still discuss and talk about improvements and then see how to do that. So it's not yet there where it could be. Oh, sorry.
Later support multiple instrumentation as a input. Can you do simulation for 2 instruments?
If you set up 2 instruments and run it through and you configure the config file, yeah, you can do whatever you like. You can even change whatever the satellite configuration, the noise floor, you can do everything.
So
If you know where and how.
the synthetic scene that would be used,
Yeah.
would be for both.
No, you have to basically, so for example, that you run it and you say you want to have an earth care output, and then it's easy. You can just in 2 command lines say, okay, please give me the same output looking as cloud side, looking as whatever, but you get separate output files.
If it can do for both instruments the same. I think this is
It's not yet the output file or the thing configured like that. It's also something you can think about. Yeah, the Doppler velocity errors basically is done on statistical knowledge or some statistical input. The first plot on top is basically the satellite motion error, and this is added during the long track convolution. So that's already added here, and so basically you get 2 outputs here, one with and one without noise. And the other noise is basically based on the statistics from Pavlos here et al. And the input that we use is basically the pink or I don't know, magenta lines, the magenta years here. And then basically, if I'm right, that's basically what you somehow see and what you get out. So on top, you see again the input data for the same scene. The input is via ground-based echo, and then we also add the ground echo here. Then in the middle one, you see the synthetic CPR, including satellite motion, where I still put a question mark here because I looked into and it looks like too good to be true. And the last panel here is the full synthetic CPR, including all the noise estimates we have.
I have a question. The synthetic CPR, including satellite motion, it's
basically one of our theories now split it in.
okay, and it is so as Pavlos mentioned, was that the motion of a satellite has a lot of vectors. Then you correct it.
No, it's not corrected. So basically, that's what I said. I looked into that and said, okay, that it's too good to be true. I looked also with Niels. Basically, Niels coded 99% of these tool here. We were looking on Friday that I plotted that and said that there is something wrong. We looked into the codes from the coding perspective. It seems to be coded right, but still there's something there that looks suspicious. So basically, I would assume that one here basically looks like without satellite motion. So because we couldn't see visually, there is no difference. If we compute the difference between satellite motion panel and without satellite motion,
Yeah, you should see that, I mean, for sure, when you enter the cloud and you go out from the cloud, I mean, that is basically including the satellite motion means including the non-uniform beam filling effects and the bias. You should always see these biases going in and out.
Yeah.
So I think, well, we can check maybe tomorrow what's going on.
But
change the velocity of the satellite, hopefully you have put that in units.
again,
No, I mean, you can change the plot of the velocity of the satellite.
yeah,
I guess is an input of your,
yeah,
and then we see how it,
yeah, it should change, yes. Yeah,
okay.
But in our case, showing the people, the users that will mainly use the level 1 or the level 2 for the validation, I mean, then we will take the corrected, the level 1 corrected for satellite motion, right? So then
It's a level 2 product.
a level 2 product. So you don't, so in the end, yeah.
There should be this additional step, yes, well. Anyhow.
Yeah, so you need this, the one without promotion, just with the all the steps you mentioned before, the surface and over here and there. And the noise is what I saw in the care data for the W. This is representative, the noise.
I don't know, that was my question basically also to Pavlos, because the plots you showed in the meeting with ESA, it looks less noisy than whatever. Okay, okay.
Well, so this is one is at 500 meters.
But
How much meters is that?
it's 500 mean a long track and 100 range.
Is it expected to have so much noise in the surface? The surface, shouldn't the surface be less noisy because it is more reflective?
It's not really nice in the sense, it's the color palette is from blue to.
Yeah.
If you never accept this happen, meter. Whatever you see, will go plus and minus 1, will go from deep blue to yellow. So that is.
Yeah. Yeah, what we also try to,
Yes, if he does that now, as you have, we have the flag, right? There's an area from here.
yeah, these are flags here for Doppler velocity folding, depending on the Nyquist. That's multiple scattering we try to estimate, and there's a flag, and there's a non-uniform beam filling estimation, so that's there. But we don't have a flag there to say.
Are you showing the velocity only for the fields above certain values?
No,
So you're showing all the velocity.
I showed all the velocity.
So none of these values are noisy just because of the regular.
Yes.
So we don't do that in the products, we don't show effectivities, velocities are very low effectivities because we don't.
Yeah.
Go back one slide.
These edges are wrong, that is, we don't have Doppler.
Yeah. If you go back
Another one.
sorry, another one,
Yeah, I know what you mean. The reflectivity is
so
here.
as I said, basically here well, the scale will be about -21 meters, -20 meters.
Yes.
So this means cyan.
Yeah.
Only over the cyan, yellow, and the blue you will not get anything.
Yes. Yeah.
Okay. Oh.
So you mean that in the end, one should, when
Basically,
you compare this, you should use also the masks and keep only the data that they are not masked to compare. This is
Yes.
what you will get.
yes.
If the data can see -25, it doesn't mean the Doppler is good and minus. The Doppler is good probably above -20.
Yes, and something like that is in the output not implemented, but basically the recommendation when I started looking into Doppler was always everything less than -15 is like.
But when you put okay, then I have another question because that's a good way. So when you put in the next, the noisiness of the Doppler.
Yes,
Again,
yeah. Can I? Or
Yeah, that's function. Okay, that function is a function of SNR, right?
yes,
You see that, right? Okay. Yeah, you plug in that function.
yes, function. Yes,
And that function is a function at a given integration length. So this is
Yes.
700 meters.
yes,
Okay. Okay.
yes.
Okay.
So this error, there's not masking for value, it doesn't look crazy in the edges.
Yes. I bet. Yes. So basically, that is always the same thing here. Of course, it looks crazy at the edges, and sometimes even you see that also when you get, like, for example, holes in the cloud curtains, and you see that the reflectivity goes down again there, and we also get like crazy values again.
If the Doppler looks like that, that's good Doppler.
That one here.
Yeah, that's what we get. That's what we get at the rotation.
Yes.
Data in the extra steps of processing will give you someone who's pretty useful. It's not magic. It's still
But yeah, basically that's what the simulator gives you out.
So it gives you that. The simulator gives you right now a single Doppler reference.
Yes.
Doesn't have a level 2
Yes.
There is, but in the disk, there is the plan to maintain this product, this.
And something also I played a little bit around. It's very fast thing that I did, or basically what you can do, sorry, to make it the other way around. The code also gives you the possibility to plot CFETs right away from all of the different steps that you, for example, want to have, or from the output or the input data. So here it's just an example of the whole scene you see above. So basically all the data on the top row is here. On the left, the reflectivity input as a 2D histogram. On the right, the Doppler velocity input. It's just cut it for the Nyquist range, and below the row for the synthetic output of the data. So basically, it's the 2D histogram for the synthetic reflectivity output.
And then this is the.
And there is no noise clipping, there nothing. That's basically, so if you look to that one here, it's basically that product.
Then this is what Pablo showed before, how you try from this to go to meaningful products.
Yeah, we were expecting it to do. Because the radar was not designed from the beginning well.
Yeah, and what you can also do.
This radar here will never do the radar. Right? So, but 20 years ago, I don't think anybody understood the thing that was doing the Doppler at all. Okay, they thought there's gonna be something straightforward. It's not that platform would be destroying effectively the Doppler. That came to life probably a decade into the future.
Well,
I mean, this is all. This is all.
we didn't know the paper at that time. Yeah.
This is also the problem with the airborne platform. For example, for the Doppler for Halo. For Halo plane, they had in the beginning the.
Different problem.
It's more the
Especially the macro is extremely more quiet, stable than any other.
in control the
Footprint that kills everything.
Yeah.
And the light moves with 7.5 kilometers per second, right? It's not with a few hundred meters.
so the spectral width is that's the widening due to the proportion to the velocity. So if it is
Platform.
on the platform. So if the remember, let's get it moving 7.6 kilometers per second, and our craft is moving at 300 meters per second, 150 velocity. So it's a factor of 20 there. Nice.
And it's also higher in space. I mean, rare in them.
Pointing, the control of the pointing, I mean, we control perfectly the pointing. Almost. Tens of micro rods. Control.
Good piece again. I mean, we should do some cleanup on this process. It's not even terrifying because like I don't know this. We know it's
Yeah.
4 months within.
Yeah. Yeah, same here for simple scatter plots. That's on the x-axis is the input reflectivity, and on the y-axis on the left is the CPR, synthetic output, and here it's the Doppler velocity. So here it's the input Doppler velocity on the x, and the Doppler velocity including noise on the y-axis. This is a scatter plot. And basically, yeah, it's you can basically see that the satellite motion, the broadening of the platform basically broadens the whole 1.5 meters per second input into everything.
So this now, it has,
Yeah, that will do all this processing. And this, I said, will go down to 0.4, which will be used for input for.
Yeah.
so Pavlos, this now you have it, so then this reaches to level 1, but then the couple things, I mean, how do you expect this to be used for the Kalman
The
signal?
Kalman things will get first raw data. And I know that the raw data will just back out 6 months. And we'll have exactly this kind of quality. Just wanted to see it somewhere. But in 12 months, now, we have an opinion, we have the CCD, what we have it much more. We want to be tested better. We know we can do much better. We knew exactly, I mean, what is impressive is that the Doppler from FKR comes exactly as we expected it. And a little bit better than all. So.
From these 5 days of measurement, you mean?
Yeah. This is.
Can you comment on what is the status of the CPR?
No. Oh my goodness.
Did I miss?
No.
Basically, how or what to do to use it. Basically, the whole code is in the GitHub repository that you will find here, or you can follow also inside of the Earthcare convolution and all the forums. There's also the link to it. There is an instruction how to install it. There's a Jupyter notebook with examples which you can run and basically produce some of basically all the examples I will show in a couple of minutes. There is an example folder provided with all the responsible input data. So basically you even don't have to download them by yourself separately. Basically you can click here, also on the link which is on GitHub, and then you can start from there and play around with data. Find more superior quick looks or things we have to do. Or you basically go to Arcturus and to ARM, download whatever you want, longer data sets, and run it. The only thing what you then have to do is to define your config file yourself, which is not really so much problematic, and you might have to look that the folder structure for reading it in is as you would expect it, or as the code expects. Yeah, the same things again, and basically just some of the examples which are in the paper I tried to submit, or we submitted last week together with Pavlos and some others. I just took the chance to look into some of the cases there, to look and to see a little bit. It's all based on the already known input data from Joyce from the 6th of April. And what we already have discussed, or we already talked about, is that the cloud boundaries are smoothed and stretched a little bit. You get somehow smaller reflectivities, and you lose some of the smaller features and cloud structures. When it comes to Doppler, in that stage I present here with all the noise stuff, you see there's a lot of noise due to what also Pavlos said, satellite motion, low signal to noise ratio, non-uniform beam filling effects. But something what you also, or what we didn't reproduce so much, so there's only this multiple scattering flag, that some of the high reflectivity cores here, for example, here, if you look to B here, there might multiple scattering be occurring, and so often cases you might flag out and can't use. Yeah, here I just want to also point out that that one is really like, at least from all I know from the looking into the data, pure winter convection. So there isn't any layer visible, and the ground temperatures were like 0 degrees Celsius. So you could look into that, then basically neglect some of the liquid attenuation where you usually also filter out data. Then something about low-level clouds. So here is a case from the ESCOS campaign from ESA and also from the 15th of July. It's also during the campaign there was the W-band radar there. And it's a little bit a repeating story, I would say. So really you see that the boundary is smooth. You lose the fine structures. Then a lot, because you have so many small scale and so many high fluctuating reflectivities, you also have a lot of non-uniform beam filling you have to correct for or look into what causes problems. So that means the more yellowish, the more non-uniform beam filling you can expect. And also because the Doppler velocities, if you look to these low clouds here, there's a lot of basically noise, because the signal to noise ratio in these low boundary clouds of marine clouds is really low reflectivity, so high signal to noise ratio. And for the Doppler, we have then to wait for the other products to see what we can get. There's an example for airplane radar data inputs. So it's basically from colleagues who flew over the Arctic, so near Svalbard. And on top you see the input data. You see that also here you have some small scale variability and some whatever convective updrafts there, I don't know. And these might be also loosen in during the earthquake might stretch that also, the same story again. But you could also see that it also leads to a lot of non-uniform beam filling effects, because there are so many gradients in a very short amount of time for the input data that really changes. The things we use basically numerical weather simulation over also Ny-Ålesund, which is in the Arctic, and transform that using the PAMTRA simulator into radar output. That's the first row in A. And then basically I run these through the simulator to produce EarthCare output, which is seen in B. And the same you could do also for the Doppler velocities here. So C is the input Doppler velocity after the forward simulation into the radar space, and D is the corresponding Doppler velocity from space. I have to say that is, first of all, a cool feature, because you could try to plug it to all kind of output data. Something what you could see is that the let's call it high resolution of the input data, which is around, I don't know, 600 to 700 meter each profile as an input. You could see that also leads to a very smooth input field, which reflects into the non-uniform beam filling estimates being really smooth. So basically the reflectivity gradient here might be not represented well. You can see that the non-uniform beam filling there is really at the cloud edges and at the cloud holes. There you get these yellowish estimations, but you don't have all these small scale features which we had above. And basically, something I also played a little bit around is using statistics and filtering data out. So basically, I'll really look into how the statistics change or what the different you can see by looking into forward simulated data. So the first two columns, let's say it like that, is always on top the synthetic output of the simulator. The first column is the reflectivity, the second the Doppler velocity, and that's basically, I didn't do any filtering. I just did the 2D histograms for 3 months of data for Joyce. First the reflectivity, second the Doppler velocity, just to compare to see how different they behave. And the second, so the column here, the third one is I used the target classification from CloudNet and basically kicked out all the columns that include liquid. So basically it's pure ice. And what I did in the last column is I allowed liquid. So basically I looked into all columns which say there is, what was filtering there again?
Liquid.
No, it was only liquid in, so basically where I had liquid precipitation present. So basically the opposite. So that's why we have also the ice part above. But basically that's the thing we don't want to see, because we can't use these data because we don't treat the liquid attenuation correctly in this model. But just to see that you have to be careful and to look really into what you represent and what you compare with what, play around and see how the differences look like.